session. Oh. Okay. Oh. Just a moment. So, I want to start this lesson by a brief summary about the properties of beta-lactam compound.
So I had a question.
Yeah?
About the character.
Yeah?
Just a question because I saw that there are two types of numeration, and so we have to follow the numeration from the nitrogen or from the sulfur. So
From the sulfur. Yeah, but you
because
could,
on this slide the number are always nitrogen.
yes, you can use both, but normally starting from sulfur atom. Yes.
So one. So
one, yes, 2, 3, 4, 5.
Another direction.
No, no, from nitrogen, okay. Right, from nitrogen, because you have to go in this.
So one from
nitrogen. Yeah. Position 5 and 6 with the 2 hydrogen, and position 3 with the acidic function.
Okay.
Yeah, okay. And this, yeah. So you can see how we can use this software. It's not difficult. Okay. This is the basic unit of penicillin. Is 6 aminopenicillinic acid. But I want to discuss about the stability of this compound. First of all, the reactive center is located here.
But we are not sharing the screen.
Okay. Now?
Yes.
Okay. So, the reactive center, the reactive atom, the more reactive atom of the whole nucleus of the whole basic unit is this carbon, and so we can put a partial positive charge here. And so, if you remember, there is the lone pairs on the nitrogen atom, but these lone pairs is not shared with the carbonyl group. And so the result is that this carbon atom is located between two more electronegative atoms, the nitrogen and the oxygen. So this carbon atom can be attacked by, for example, nucleophiles, Once again, nucleophile can have basic electrons, and so we can have this type of attack.
Just a question, how it's called, the software?
Can grow. There are different nucleophiles in bacteria. The main target of the beta-lactam compounds are an enzyme called transpeptidase, and this compound is involved in the formation of the peptidoglycan cell wall, if you remember. But there is also another class of enzymes called beta-lactamase. Also, this class of enzymes has a basic lone pairs. These enzymes are characterized by basic functions, able to open your beta-lactam rings. This is the problem, that a lot of bacteria are now resistant because they develop this class of enzymes in the cell wall. And so a lot of beta-lactams are opened, are deactivated by this class of enzyme. There is another important topic about the chemical stability of this nucleus, of this compound, 6-aminopenicillinic acid. What happens in basic condition? What happens in basic condition? You know, OH minus is a nucleophile, and so it is able to open, to react, to attack the carbon atom, and to open the beta-lactam ring. This means that all penicillins are not stable in basic condition. But what happens in acidic conditions? We are interested only in acidic condition because if we want to take an beta-lactam penicillin orally, you know, in the stomach the pH is about 1.5 pH unit, and so this compound should be resistant to the acidic condition in stomach. So I want to show you what happens in the acidic condition. Here you see the side chain of penicillin, for example. Okay. So we are in acidic environment. You know that normally protons search electrons. And on this backbone, there is an atom with a lot of electrons. Yes. In particular, you see this nitrogen atom of the beta-lactam ring has a lone pair. So normally, this nitrogen atom can be protonated by in this case, you know, the nitrogen atom assume a positive charge. This means that we increase the electrophilicity of the carbon atom, of the reactive carbon atom. This means that this carbon atom can be attacked by the oxygen or the middle function inside chain. So you can understand how normally a penicillin is not stable in acidic condition, because you have an intramolecular attack from this oxygen atom inside chain, because this carbon, the carbonyl, is now more reactive. Is it clear? Have you any questions? And another question is how we can increase the stability of this compound in acidic condition. What kind of modification we have to perform on the molecule, on the benzyl penicillin, for example, was the first one. So we can here an aromatic ring in this position. Okay. This is the first penicillin discovered by Fleming. This penicillin is not stable in basic condition, no, because the OH minus can open the beta-lactam ring, we have seen. But also in acidic condition is not stable because after the protonation of the nitrogen atom or the beta-lactam ring, you can have an attack from this oxygen on the carbonyl compound with the opening of the beta-lactam rings once again. How we can increase the stability of this compound in acidic condition? In that time, there were two different classes of scientists. The first one want to insert another acidic function on the side chain, and the second one wanted to introduce an amino function. In that time, the scientists wanted to increase the spectrum of benzyl penicillin, because at the beginning benzyl penicillin was active only against gram-positive. And so they try to increase the hydrophilicity of benzyl penicillin in order to increase the spectra of this type of compound. But why they decide to introduce two hydrophilic residues? In that time, they wanted to increase the activity of these compounds against the gram-negative. And if you remember, gram-negative, they have a more complex structure, an additional external membrane. The cell wall is covered by this external membrane. So gram-negative, the transfertidases, the target in gram-negative can be reached hardly by these antibiotics, by this penicillin. So they decide to introduce these two hydrophilic residues because they thought to cross the external membranes through the aquaporins. If you remember, aquaporins are important for the cell line, because water, salt, sugar can cross the membrane directly through this type of channels. So at the beginning, this was the first reason to justify the introduction of this type of substituent in the structure of benzylpenicillin. But later, only one of the two classes was lucky. Not the first, because if we assume orally this type of penicillin, carboxypenicillin, you know, with this additional carboxylic group, in stomach, in acidic environment, we have the decarbostylation of this COH. So the molecule can lose this important substituent, and so we have again benzylpenicillin. A moment. You see, we have again benzylpenicillin in our stomach, and in our stomach benzylpenicillin is not stable. So carboxypenicillin is active against gram-positive and gram-negative, but we can use this type of antibiotics only by injection, because at pH, physiological pH 7.4 is stable. And so we have to introduce directly in the bloodstream this type of compound. And what happens on aminopenicillin? You see? We can assume this compound orally, yes. And what happens in our stomach? We can have the protonation of the basic nitrogen atom on the side chain, And we are in the stomach, where a lot of protons are present. And you can see that the protons have the same charge of the protonated nitrogen atom. So this means that this protonated nitrogen atom can defend the beta-lactam ring from the attack of the proton, because they have the same charge, and so we have a repulsion of the two species. So the presence of this basic function in the side chain increase the pharmacological properties of this penicillin in two different ways. First, we have a more hydrophilic compound able to cross the membrane of gram-negative through the foreign channels. So we have a wider spectrum. And the second reason is that the presence of this basic function, protonated in the stomach, can protect, can defend the lone pair of the nitrogen atom in the beta-lactam ring by the attack of the protons. So you can understand that aminopenicillin represent one of the most important penicillin used orally. And in addition, they introduced also another hydrophilic group on the aromatic ring, giving the amoxypenicillin. Aminopenicillins, amoxy, no amoxy because we introduced OH, a phenolic OH group, just to increase the hydrophilicity of this class. The problem of the aminopenicillins is not related to their stability, because they are stable in acidic condition, physiological pH. They have a wide spectrum against bacteria, but the problem is related to beta lactamases. These enzymes are able to open, to attack, first of all, to attack the carbon atom of the beta-lactam ring and to open the ring. And so, more than 20 years ago, there were a lot of strains of bacteria resistant to this type, to the aminopenicillin, to the amoxicillin, because they have a very active enzymes, beta-lactamases, on the close to the surface of the cell wall. But now, amoxicillin is still on the market. It's one of the most sold antibiotic compound because it was associated with inhibitors of beta-lactamases. We'll see at the end of this chapter that there are some molecules very close to the penicillin that are able to interact with beta-lactamases and to block their activity, and so amoxicillin can remain intact, can remain still active, and so can attack, can kill bacteria. This is one of the modern strategy to use whole drugs. We know everything about these drugs. We used for years. We have been used for years this type of drugs. Hello, prego, buongiorno.
Buongiorno, conto solo gli
Sì,
studenti.
sì, prego,
Grazie.
prego. And so we can use again this type of antibiotic in association with inhibitors of beta-lactamases. In particular, we'll see the structure of clavulanic acids, but at the end of this chapter. So, have you any questions about this point? Is all clear for you? Chemical reasons are clear? Okay. So, now, if you remember, we have to describe how we can obtain 6-aminopenicillamic acids. So, starting from benzylpenicillin. So, okay. Yes. This. So, starting from benzylpenicillin, we have to obtain 6-APA, APA, 6. This means that we have to hydrolyze this amido bond, sorry, exocycle, amido bond. If you remember from the organic chemistry, an amide is stable. If you want to hydrolyze an amide, normally we can take a basic solution, or in acidic solution, and warm.
Okay.
And warm,
Okay.
because they are quite stable in comparison with an ester. But the problem is that on the same molecule, we have 2 amide functions. One is exocyclic, outside the cycle, and the other one is the beta-lactamic function. A lactam, you know, is a cyclic amide. And so if we take benzylpenicillin and we treat this compound in a basic condition, and the result is to open the beta-lactam ring and also, okay, to hydrolyze the other amido function. Yes, I know, but we lose the activity of the compound. So we have two same functions, but only one should be hydrolyzed. The other one should remain intact. And so in that time, the scientists try to find the right way to hydrolyze only the external amido function. How? Is there any difference? Are there any difference between the two functions, in your opinion?
One is tertiary, one is secondary.
Please?
One is tertiary and one is secondary.
This is the first one, and this is the second one. You see here. You see you have NHCO and another NCO.
So the lower is the carbon. One of them has the carbon also.
Yes, you have also the carbon here, so we can
Yes. Sorry.
we can have, you see, in this case is more reactive, and so if you treat with the OH minus, at the beginning you open the beta-lactam ring. But please, you see that there is a mobile proton here. And perhaps from organic chemistry, you remember that keto-enol tautomerism. I don't know if you remember, it's like now, I'll show you what happens. When you have a mobile proton, we can have, just a moment. You see, the proton can be shifted on the oxygen. Keto, I write to you. Keto-enol tautomerism. Keto means the carbonyl, enol means alcohol. It is not resonance. Resonance is a shift of electrons. In this case, you have a shift of a mobile proton. In the beta-lactam rings, you have no any mobile proton, you see. So, if you record an NMR spectra on a benzylpenicillin, you see a peak of this alcoholic OH, because normally about 20–30% is in an enol form, and 70 is in a keto form. So part of the benzylpenicillin is present in enol form. At this point, you can treat this enol with a reagent able to transform the OAH in an halogen. So PCl5, for example, you have the substitution of the OH group with a chloride.
Could you repeat it? What's the way to treat it?
Yeah, PCl5, you see, is phosphorus pentachloride. Yes. Or you can use thionyl chloride. All these compounds, thionyl chloride, phosphorus pentachloride, are reagents able to transform an OH in an halogen, in a chlorine atom in this case. We can use also phosphorus tribromide is the same. We can transform the OH in a bromine. But what we want is to transform, to activate this OH in an halogen. This means that we increase the positive charge on the carbon atom, because you see you have an halogen. Halogen is more electronegative than a carbon atom. And so we increase the charge, the positive charge on this carbon atom. After that, we have the reaction normal butanol. Why? This alcohol. If at this point I add water directly, I have not the hydrolysis of this double bond, of this imino bond, but I come back again to the enol form. So I have to use another type of water derivative, an alcohol, in this case. This means that the oxygen group can attack the positive carbon atom, and we get, just a moment, no. Ooh, no, doesn't work, just a moment. Oops. So So we transform the chloroimine in amido ester. You see, it's like an amido ester without chlorine. Just a moment. So normal butanol is able, is a nucleophile, is able to attack this carbon atom to give this imido, you see the double bond ester. This means, okay, you see here. This is an ester, if you remember. In this case, you have the long chain attached to the oxygen here, and a double bond with oxygen. In this case, you have a double bond with the nitrogen. So it's an imido ester. At this point, we can add water to hydrolyze the double bond. And so we get the final compound, this one. The 6-amino-penicillinic acid. This thing, okay, there is, if you see on the synthesis on the slides, here, just a moment. Oops. Doesn't work. Okay. If you see this slide, you see at the beginning the treatment with the phosphorus pentachloride, but the first step is represented by the protection of the acidic function. Okay, just a protection, it's not so important. The important point is how we can hydrolyze this type of amide and not the beta-lactam ring. This is the most important time of this synthesis. And we are able to introduce an halogen atom on this carbon because we exploit the keto-enol tautomerism. You can see here, because there is a higher degree of keto-enolic tautomerism in the exocyclic amide than in lactam that cannot tautomerize. This is the main reason. So no resonance, but thanks to the presence of this mobile proton, we can have the enol form with OH, and so we can introduce the chlorine atom, an halogen, to activate this carbon atom in order to have a higher, a more potent positive charge on this carbon atom, and then we introduce normal butanol and then water. Have you any questions? Please, yes.
Could you repeat why do we use the alcohol?
Yes, okay. We have introduced a chlorine atom, okay? If we use at this point water, okay, directly, we come back again on the enol. And so we have to stabilize this form by introducing a stable oxygen derivative like normal butanol. It's clear now?
Yes.
Okay. Have you any other questions? If you see on the slides, you can see some chemical structure, but during the lesson, I can explain you all reasons, all steps, step by step, just to apply your knowledge in organic chemistry. You see here in this picture the keto-enol tautomerism and how the amido function in the ring is not able to have this type of chemicals structure. Yes, no enol, nothing, because there is no mobile proton here in the ring. When we have 6-aminopenicillinic acid, it's possible to transform it in the different type of penicillins by activated carboxylic acid in order to change the structure of the side chain. But we have already seen this part, I think. And so I am not interested in the different activation of the carboxylic acid, but just to show you that there are a lot of different ways to activate the carboxylic function in order to react with the amino group in this position. During the last lesson, we have discussed about the approach to increase the resistance towards the beta-lactamases. Okay, we can use once again here. So we can cancel out this. If you remember, beta-lactamases are enzymes with a basic group able to attack the positive carbon atom on the beta-lactam ring. We have seen some penicillin with big substituents, for example, on the aromatic ring. The electron clouds of these substituents can protect the beta-lactams from the attack of the beta-lactamases. You know, the electronic clouds have negative charge. Beta-lactamases have lone pairs, so negative electrons. The two clouds have the same charge, and so it's possible to protect the beta-lactam ring from the attack of the beta-lactamases, because these two clouds are repulsive, you know. They have the same charge. This was one of the first solutions, but in that time they found also another solution. Represented by the presence of an oxygen atom on the side chain. Why an oxygen in this position? Why this oxygen is so important? Why this oxygen is able to defend the attack of beta-lactamases? From the attack of the beta-lactamases. Oxygen, you know, is electronegative. You see. Sorry, this oxygen defends the beta-lactam from the acidic environment. Sorry, not from the beta-lactamases. Sorry. So why this oxygen is able to defend the penicillin from the acidic condition? So, sorry. Once again, I remember you the presence of the lone pair here, the protons here, and once again I remember you the protonation of this nitrogen atom, and so also the possibility of this oxygen to give an attack to this carbon atom. The presence of this oxygen, more electronegative, can decrease the total negative charge of this oxygen. So, in this way, you see this oxygen is more electronegative, and can decrease the total negative charge of this oxygen of the exocyclic amide function. And this oxygen is no more able to give an attack to the carbon atom of the beta-lactam ring. This penicillin was the first penicillin stable in acidic condition, and so in that time people used this type of penicillin VU, it's called. Phenospen is the commercial name. They use this type of penicillin orally. This was the first example of penicillin that can be used orally. After this penicillin, the second series stable at acidic condition were represented by aminopenicillin. And so we have already described the resistance of aminopenicillin in an acidic condition.
Bro,
Yeah.
I just have a question. I don't understand something. This oxygen will decrease the total negative charge.
Of this you see of this carbon.
Okay, but why? Because they said.
Because in other case, if you have the protonation of this nitrogen, you have a positive charge here. You can have an increased electrophilicity of this carbon atom that can be attacked from the type of oxygen. You see here?
Okay.
If you decrease the total negative charge of this oxygen, we can block this type of effect. In that time, a lot of different penicillins were synthesized, but only a few number of them was used on the market. So you can see here on the slide. A moment.
So the penicillin with the bulky group is to avoid bacterial resistance.
To beta lactamases.
Okay, and the one
because you have a negative cloud just around the beta lactam ring. Yes.
And the one with the oxygen is to increase the stability in the
acidic
environment.
yes.
To have a
Yes. Okay, here you can see the two examples of the more hydrophilic penicillins, aminopenicillins, called also ampicillin, and the carbenicillin, carboxypenicillin. Here in the picture, you have a representation of the aquaporin. So you can see that this compound, this hydrophilic compound, can reach very easily the peptidoglycan in the gram negative. Okay. After the discovery of the benefits of the amino function in the side chain to give a acidic stable penicillin, the scientists try to introduce other modifications on the side chain in order to increase their activity, antibacterial activity. In particular, they introduced another hydrophilic function on the aromatic ring, and we got in that time amoxicillin, more hydrophilic than aminopenicillin, ampicillin. But the second problem was related to the, where is the camera? The second problem, you see, just I want to describe the second problem because it is important. Just a moment. Okay. we have an amino group here. Another problem of this aminopenicillin is related to the presence of the acidic group, okay, but also you can see there is also an amino group on the same structure. It's like an amino acid, if you remember. Amino acids are particular compound with two different functions, an acidic function and an basic function. This means that this aminopenicillin, ampicillin, are ionized at every unit of pH. Because if we are in acidic condition, you have the protonation of the basic nitrogen atom. So you have a positive charge, in this case here. If you are in basic condition, you have the ionization of the acidic function. In this case, you have a CO minus. So at basic pH, you have a minus charge in this position. In acidic condition, you have a positive charge. This means that this molecule is not absorbed in an ideal way because it is charged at every pH unit. If you remember from the introduction part, the charged molecule can cross the membranes very hardly. Because if you remember the chemical structures of the membrane, they are formed by two different layers of long carbon chain, phospholipids, and so on. Okay. So the scientists decided to mask one of these two functions, in particular the acidic function, by transforming this function in ester, for example. You see here, you have a double bond here, oxygen here, another oxygen here, and another. Why in an ester? Because if you assume ampicillin in this form, it can be absorbed very easily in the intestine, where pH is higher than in the stomach. After that, the esterases, ubiquitous enzymes present in the whole body, can hydrolyze this ester function and can release again the free ampicillin.
So can you repeat after the absorption in the intestine, what will happen?
Here, after the absorption of the ester form in the intestine, this ester can be hydrolyzed by esterases, which are ubiquitous enzymes present in all body, in all districts of our body. In this case, we can improve the absorption of this antibiotic by transforming the ampicillin in its ester, in an ester, to mask ionizable function. There was also a third modification of the structure of aminopenicillin, where on the basic function here, the scientists thought they saw that an increase in hydrophilicity is responsible of an increase in activity. So they thought to increase the hydrophilicity of the aminopenicillin by introducing on the side chain the residues of urea. You see here the chemical structures of urea.
Where they introduced urea?
Yeah, just now, just a moment. In the side chain on the basic nitrogen atom. But now I show you the chemical structure of urea. You know this compound is present in our urine. It derives from the metabolism of amino acids, of proteins. It's a very hydrophilic compound, very common in agriculture, used extensively in agriculture to increase the growth of the plants. And they introduced this residue here on the side chain. Just a moment. You see these residues of urea in the side chain, just to increase once again the hydrophilicity of penicillin. And we have now the ureidopenicillins. Ureidopenicillin. This type of penicillins are active against gram-negative, but are still sensitive to beta-lactamases. So they are not resistant to the action of these enzymes. So three modifications to the chemical structure of aminopenicillin. The first one was the introduction of an OH on the aromatic ring. Okay, you remember this point. Amoxicillin. The second was to mask here the acidic function with an ester to increase the absorption. And the third one was the introduction with a residue of urea in the side chain in order to increase the hydrophilicity. Three important modifications to aminopenicillin. Okay. Just a minute. You see the first modification, the OH. You see this quite strange alcohol using the esterification of the acidic function. Okay, I'm not interested in the chemical structure of this particular alcohol, it's just to describe you how the introduction, how by masking the acidic function we can increase the absorption of this type of compound. And the third modification is related to the introduction of the urea residue in the side chain in order to increase the hydrophilicity once again. You see here the uridopenicillins, you see in red the residues of urea. I am not interested in this type of difficult compounds, but I think you have to know the chemical structure of aminopenicillin. This is very important. Okay. So 5 minutes and then we stop. Sometimes it is necessary to have a stable and a long-term concentration of penicillin in blood. For example, for 2-3 months. So it is necessary to maintain a low concentration of penicillin in the blood for the therapy of particular infections. You can understand that it's not possible to make an injection every day. And so the scientists prepared particular salts of penicillins with particular bases in order to have low soluble salts able to maintain a low concentration for the long time of antibiotic of penicillin. Normally, this retarded, you see, retarded form, depot, reservoir form of penicillin are injected once a week. And normally you introduce about 10 milliliters of antibiotics. And they use a particular base, you see here in the picture, called procaine. You see the basic nitrogen atom here. This nitrogen atom is able to form a salt with the acidic function of the penicillin, and so you have a salt. But the procaine is also a general anesthetic. So when you inject this type of formulation, you have normally a strong pain. In this case, the pain is controlled by the presence of propane, which is a local anesthetic. So we can control the pain thanks to the presence of this local anesthetic. These are called retarded penicillins, very useful for the therapy of particular infections. Here we have the last feature of penicillin. We have already described some the stability of the penicillin. You see here what happens in a basic conditions. You have the opening of the beta-lactam ring, or in the presence of beta-lactamases, you can have the opening of the beta-lactamases or the beta-lactam ring. Yes. Loss of carbonic anhydride, and so you get phenyloic acid. This in basic condition. In acidic condition, the situation is more complex. You see the protons, which want to take the lone pairs from the nitrogen atom. You can have the increase of reactivity of this carbon atom, which can be attacked by the oxygen in the side chain in order to give the azelacton here. After that, you have the demolition, the destruction of the structure of this azelacton to give penicillamine, phenaldic acid, and so on. The two important points is related to what happens in basic conditions, the opening of the beta-lactam rings, and in acidic conditions you have the same, the destruction of this reactive ring. So, have you any questions about penicillins? Atom, I don't know. Atom, have you any questions?
No, it's clear.
No? Okay.
Thank you.
Okay, Jeanette. So, okay, so 15 minutes of break, okay, and then we start again at 35. Okay. So we have seen the chemical structure of penicillins, their stability, their pharmacological activity, and now we have another family of the beta-lactamics antibiotics called the cephalosporins. Cephalosporins were discovered in 45, and the first the first cephalosporin isolated is called cephalosporin C. You can see here the chemical structure of these natural compounds. Once again, you can see the 4-ring cycle, the beta-lactam ring, but in this case is fused with a 6-member ring. You see dihydrotiazine, sulfurazine is nitrogen, and once again you see an acidic group here, the side chain, and here you can see an ester group, and normally in this position we'll see the good living group we need in this position, this type of group. The last time I showed you the model of the cephalosporins, and in this case the 2 rings are on the same plane, and if you remember the penicillin, the situation is quite different because the 2 rings are almost perpendicular. But the reactivity of cephalosporin is due by the presence of this leading group and this double bond. In fact, you can see here what happens when the nucleophile, for example, the transpeptidase, the main target of this family, attacks on the carbonyl, on the carbon atom of the carbonyl group here. You can see the opening of the beta-lactam ring, and the lone pair of the nitrogen atom, you see, is shifted on the 6-member ring, and due to this double bond, conjugated double bond, we have the formation of this unstable 5-methylene, this carbon atom with a double bond here in this position. So in this case, the reactivity is not due by geometric features of the molecule, but by this shift of electrons. So thermodynamic is based on thermodynamic reasons, and the product is this unstable dihydrotiazine. Here you can see how it's possible to get cephalosporins from penicillins. It is not, this synthesis is not required for the course, but is just to show you how it's possible start from a 5-member rings and to enlarge this ring to a 6-member ring. In this way, you see here the different steps. The synthesis is quite difficult, but it's just to explain you that it's possible to have cephalosporin starting from penicillin. This means that we can start from benzyl penicillin, natural compound, to get the 6 aminopenicillinic acids, and then to enlarge the 5-member rings to 6-member rings in order to have the basic unit of cephalosporins. This is an important point, because otherwise it is very difficult to have cephalosporins directly from natural compounds. So we have a semi-synthetic approach. We can start from penicillin. We have a lot, big amount of penicillin to have cephalosporins. Okay, just a moment. I have to change the file. Just a moment. So now we start with a description of the different classes of cephalosporins. But at the beginning, I want to show you the stability, the chemical stability of this class of compounds. This is the cephalosporin C. It was the first discovered the cephalosporin, and you can see the configuration of the carbon of the chiral carbon atom in position 6 and 7. The configuration is the same of penicillin. It's just different in the number because we have a 6-member ring. The configuration is the same. But how cephalosporin can be disactivated? First of all, you can see that in basic condition, the OH minus can open the beta-lactam ring. We have already seen this factor with the penicillin. But also esteresis. Esteresis is another class of enzymes, of ubiquitous enzymes present in our body. And esteresis are able to hydrolyze this ester group, which represents a good living group, an optimal living group, and because it is necessary for the biological activity to have a good living group in this position. And the esteresis are able to hydrolyze this ester to give this alcohol function, which can be form a lactone. A lactone is a cyclic ester. And so esteresis is another class of enzymes able to inactivate this type of compounds. Also, in basic conditions, we can have the opening of the beta-lactam ring, but also the isomerization of this double bond. You see, this double bond can change its position, and this isomerization can lead to inactive cephalosporin. So we have to pay attention when we are in a basic condition, because we can have the opening of the beta-lactam ring, but also the isomerization of the double bond. We have seen for penicillins different classes of penicillins characterized by different modification of the chemical structure. Here, in the case of cephalosporins, we have different generations. This means that we start from more than 30 years ago, and then we have different generation with a different activity towards, at the beginning, towards gram positive, and then at the end, only towards gram negative. Once again, we'll see that these biological activities are related to particular chemical modifications in order to increase normally the hydrophilicity of this compound. First generation. We can distinguish two different types of cephalosporins in the first generation. The first type for parenteral use, by injection, and a second type used orally. You can understand, if we use orally a cephalosporin, this compound should be resistant to the acidic condition in stomach, you know. At the beginning, you see the basic backbone of cephalosporin, an aromatic ring, the side chain like in the penicillin, like for penicillin, and once again you see the leaving group represented by an acetyl. Acetyl is a good leaving group in order to have an ideal interaction with the transpeptidase in this point. But as I told you before, this ester can be hydrolyzed from esterases, and so the first modification in that time was to introduce another good leaving group, like this one. You see the leaving group is due by the presence of S- with all these heterocycle. The S- is a good leaving group, and in this case, this group cannot be hydrolyzed by esterases. Oral administration, once again, we need cephalosporin stable in acidic condition, and so in this type of cephalosporin, you can see the introduction of the amino group on the side chain like for aminopenicillin. The same strategy, nothing new. But in this case, you can see that in this type of cephalosporin, there is no any leaving group. Only a methyl, which is not a leaving group. It remains. And so perhaps the cephalosporin used orally are less active than those used by injection, because they have no any leading group. Second generation. Okay, just a moment. The first generation, they are active only against the gram-positive, like for penicillin. How we can improve the activity of the first generation? Some years later, the scientists isolated a new natural cephalosporin called cephamycin C. Cephamycin C, you see the name, and you see here the structure. Where are the novelty? Where are the new modification in this natural compound that we can apply to the class of cephalosporins? You see in red two important modifications found on this natural compound. First of all, this methoxy group under the plane, you see. This methoxy group is a bulky group with a wide electron cloud, which can defend the beta-lactam from the attack of beta-lactamases. So in this case, the scientists apply the same strategy, and on the backbone of the old cephalosporins, they introduce this methoxy group in alpha position. You see under the plane, to increase the stability towards the beta-lactamases. And the second difference is due by the presence of this amino group instead of a methyl. You see is an ester with a very strange acid. I show you this acid on the here. Just a moment.
Can you repeat the second modification?
Yeah, just now. Just a moment. We can start. The second modification is the substitution of the leading group with an ester, but another type of ester. I show you now this type of acid. Just a moment. We have to. Okay, and now we open the ring. Okay. Okay. Here we have the double bond. No. Okay, and then you see here. Oxygen, but here instead of a methyl group you have an amino group. Okay. So why this acid is so effective? This acid is called carbamic acid. Perhaps you have never seen this type of acid, but This is called carbamic acid. Why? Just a moment. The difference between acetic acid and carbamic acid. Acetic acid is a classical acid that can be hydrolyzed from esteresis. Esteresis. Okay. If we introduce the amino group, we have carbamic acids. And what happens in the carbamic acid? We can see now. There is the lone pair on the amino group that can be shared with the carbonyl compound. Just a moment. Here. Here. And so we can have a resonant form like this. We can have a double bond here. We can have a single bond, minus. And here we have a, oops, with a positive charge. So, so you see, it's like an amide, and the carbamic acid can be not hydrolyzed from esteresis. But it represents a good living group. So the scientists, starting from the chemical structure of a natural compound like cephamycin C, they decide to introduce the same groups responsible for the resistance to beta-lactamases and to esterases in some synthetic cephalosporins. You can see here, just a moment. The first prototype of the second generation cephalosporin was cefoxitin. And so you can see the methoxy group in alpha position and the amino group on the instead of the methyl group. So these two differences are introduced, these two groups were introduced on the backbone of the first generation cephalosporins. But methoxy group was effective in this position, but the scientists shifted the position, they changed the position of the methoxy group from the carbon 7 to the amino group in the side chain to give a oxime, the bond between a nitrogen atom and oxygen is called oxime, methoxyminic group. You see there is a double bond, the methoxy group can be very close to the beta-lactamase ring in Zusammen configuration or cheese configuration, because the methoxy group is towards the beta-lactamase ring, or can be in the other position in Entgegen configuration in the other side.
No,
The other
but,
side.
but which one is the oxygen?
You see here the methoxy group,
Yes.
you see here the double bond. So the methoxy group can be very close to the beta-lactamase ring. You are, in this case, we are in the Zusammen configuration, Z. Or on the other side, the methoxy group can be in the other side in Entgegen configuration on the other side. Only in Zusammen configuration, this group is able to protect the beta-lactam ring from the beta-lactamases activity. Because you can imagine the electronic clouds is just around, very close to the reactive carbon atom. And so cefuroximine is resistant to the beta-lactamases. And once again, you see also the amino group in this position to have the carbonic acid as a leaving group. Oral administration, nothing new, because amino group in the side chain, we have already seen in the penicillin. No leaving group on the dihydrotiazine ring. Third generation. In the third generation, the scientists wanted to enlarge the spectrum against gram-negative. For these reasons, they try to increase the hydrophilicity of the whole molecule. How? You see here in the structure of a cefotaxime, you see here, you see in red the introduction of this particular heterocycle, amino thiazole. Amino, you see the amino function, thiazole is an aromatic ring, okay, 5-member, with an amino group, and this amino group is able to increase the hydrophilicity, the whole hydrophilicity of the molecule. Once again, in order to have activity against gram-negative. The leaving group is always an acetyl residue, negative charge. And here you can see different types of cephalosporins with the same side chain, the same amino thiazole residue on the side chain. This increased hydrophilicity is responsible of the activity of this generation against gram-negative. So please remember only this small difference, not the whole molecules of the different cephalosporin, because I know it's like the phone book, so it's not useful for you, but just to have an idea of the modification in the third generation is represented by the introduction of this amino thiazole group by this type of oxime you see, able to give the resistance against beta-lactamases. Oral use once again, you see the same situation, oxime, aminothiazole, no living group. Fourth generation, the same heterocycle, the same oxime. The most important modification in this generation is represented by the living group. In this case, we have pyridinium residues, which represents good living group in this case. Fourth generation, cephalosporins are active only against gram-negative.
That's how it's called, the living group.
Pyridinium, you see, is like a protonated pyridine. There is a quaternary nitrogen as living group. And now, very recently, it was introduced on the market cephalosporin of the fifth generation, called ceftolozane. You see here the chemical structure. You see the backbone of the cephalosporin. You see the side chain is the same that we have already seen with the oxime, with the aminothiazole, with a very big living group with a lot of basic nitrogen atoms. This means that in this case we have the scientists increased a lot the hydrophilicity of this compound, because you can see different amino groups on this structure. So it's very important to have hydrophilic molecules in order to have a wide spectrum against gram-negative. In particular, this type of compound is indicated for the treatment of complicated urinary tract infections, resistance bacteria infection. So we can summarize all modifications performed on cephalosporins. In particular, we have seen how to increase the hydrophilicity in order to increase their penetration into the active site, how to increase the beta-lactamase stability, oxime in the side chain, pharmacokinetic parameters, okay, to have stability to the acidic condition, and also metabolic stability. Here you can see a final picture about all modification performed on the different generations of cephalosporins. In particular, you see the side chain, acyl amino substituents, substitution on carbon 7 with the methoxy group, if you remember, living group in 3 position, carbamic acid in 3 position. It's just to recapitulate all the modification performed on the different classes of cephalosporin. Therapeutic indications. Infections. You know, these are antibiotics, and so use this type of compound for different infections. Lower respiratory tract, infections, urinary tract infections, especially infection present in a hospital environment. You know that in a hospital it's very easy to take infection from resistant bacteria. Gastroenteric tract infections, female genital apparatus, bones, soft tissue, meningitis. The administration of cephalosporins is common to treat meningitis in a classroom, in discotheque, and so on. You know, it is necessary 1 tablet of cephalosporin just to treat the students from this type of infection. Septicemias and gonorrhea. But you will see the therapeutic indications in the course of pharmacology. Okay, you will see better this type of indication. So, have you any questions about cephalosporins? At home, have you any questions? No? We have seen the 2 classical groups of beta-lactam. And now we'll see non-classical antibiotics, beta-lactam antibiotics. The discovery of these non-classical compounds is related to the isolation of another important natural compound called tianamycin. You see, tianamycin. Tianamycin is a very potent antibiotic, natural compound. And here you can see the chemical structure of this natural compound. Once again, please, you see the beta-lactam ring, you see here, fused with another 5-member ring, but in this case, the sulfur atom is outside the 5-member ring, and the double bond, and there is a double bond like in cephalosporin. So, this class represents a mixed chemical structure between penicillin and cephalosporin. 5-member ring, like in penicillin, double bond, like cephalosporin. Once again, you see an acidic residue here, a very simple side chain, no aromatic rings, nothing, only an alcoholic group. Yes. But please note this particular chain on the sulfur atom, particular basic chain. This compound was very active, but the scientists tried to isolate this compound, and in that time they were not able to have pure sample of this compound. At the beginning they have an active compound. After a few minutes the activity was completely lost. And the problem is due by the chemical instability of this compound. Why? Chemical instability. Because you can see how the amino group is able to give an intramolecular attack to the beta-lactam ring. So you can isolate this compound, and after a few minutes, this compound is completely inactivated by an intramolecular attack due by the presence of this amino group on the chemical structure. So the scientists try to decrease the basicity of the amino group in order to increase the stability of this potent natural compound. The first derivative of this modified compound is called imipenem. You see here the chemical structure is the same of TNMIC. You see the same backbone, the same side chain, but you see a decreased basicity of the amino group by the introduction of a formic aldehyde. You see the shift base, the double bond, the amino bond here. So the scientists try to decrease the basicity of the amino group by introducing formic aldehyde in the structure. Imipenem is a very potent antibiotic, and imipenem is very stable. But there is a problem in the use of this compound. If we try to use this compound to treat renal disease infections, this compound is completely inactivated by particular amidases, proteases present at renal level. These enzymes,
What's the name of the enzymes?
yes, proteases present at the renal level.
And
Amidases, the same. You know, these enzymes are able to hydrolyze the amido group. In particular, these enzymes are able to open the lactam rings, because you see you have an amido group, it's a lactam, and these peptidases are able to inactivate this type of antibiotic if you want to use this antibiotic against particular urinary infections. To avoid this problem, this imipenem is associated with a cilastatin. Cilastatin is an inhibitor of this type of proteases. So we have an association of two different compounds. Imipenem is able to attack the bacteria. It is an antibiotic, and it is now resistant to the activity of proteases because it is present an inhibitor of this type of proteases called cilastatin. Here you can see the chemical structure of cilastatin, and you see in red some chemical features common with imipenem. And you see once again the amino group. And so the peptidase attack cilastatin, and they are blocked. And so imipenem can act as antibiotic. So cilastatin preserves imipenem from inactivation.
No.
Yes?
But why these proteases at the renal level, they only attack imipenem, but they don't attack the main one, the tyrosine?
No, only this, because
but
I
they
think
also have an amino group, no? So what's the difference?
I think that this type of enzymes are a very small active site.
Okay.
You see the shape and the dimension of these compounds is the shape is smaller than cephalosporins, because you know in the side chains there are aromatic rings and so on. In this case, nothing, only an alcoholic group. And so I think this compound can be interact with the active site, with the pocket present on the enzymes, and so they can be inactivated from this class of enzymes. This is my opinion. And so it is necessary to associate this type of inhibitor. Once again, you can see another antibiotic of the same class called the meropenem. You saw in blue the chemical structure of imipenem, stienomycin, and it's like when you see a new car on the market. At the beginning, you see a new car. After 2 or 3 months, you see other companies with the same shape of the same car. Here is the same. They use the same shape, the same basic unit. They change only the basic group. And meropenem is another example of this class with the same basic unit, the same backbone, with a different basic group. Okay, 5 minutes and then we stop. Nocardicin. Nocardicins were isolated in 76 from Nocardia uniformis. And they demonstrate, this class is very important because this class demonstrated that it is enough the presence of only a beta-lactam ring to have an antibacterial activity. So you can see how it's possible to simplify the chemical structure of penicillins, cephalosporins. In this case, we have only the basic unit is represented only by the beta-lactam ring. Once again, you see the side chain, oxime group. We have already seen these chemical features. And you see also the acidic group. Starting from this molecule, a new class of non-classical beta-lactams was developed. In particular, the basic unit is represented by the beta-lactam ring, only by beta-lactam ring. You see an acidic group, a sulfonic acid group, like a carboxylic acid, and amino group which can be functionalized with a particular side chain, very similar to the side chains that we have already seen in the other class of cephalosporins, penicillins, and so on. you can see the behavior of this type of ring, the chemical behavior. Once again, you can see the reactivity of the carbonyl that can be attacked by transpeptidases. And here you can see the most important prototype of this class is called astreonam. Astreonam is the most potent beta-lactam used against infection. It is used only in hospital to avoid the formation of resistant strain. And which is the chemical structure? Beta-lactam rings, 4 atoms, acidic group, sulfonic acid. Side chain is the same of the most potent cephalosporins. You see the amino-thiazole group, hydrophilic aromatic ring, and the oxime, carboxyalkyloxime, you see, able to defend the beta-lactam rings from the attack of the beta-lactamases, because these oxime form a special shield, a special cloud, electronic clouds very close to the reactive point. So really, astreonam is used only in hospital, just to, it represents the only weapon that we have now against the resistant strain of bacteria. And so it was assembled by different pieces. You see different residues. The aromatic ring from cephalosporins. The oxime, okay, we have already seen in cephalosporins, okay. The 4 membranes from this class put together, and we have a very potent antibiotic against resistant strain. Just 2 words against beta-lactamases. There are different classes of these enzymes, yes, but I want to show you how these enzymes are able to open the beta-lactam ring. These enzymes are characterized by the same active site of transpeptidases, a serine. You see a serine residue, an O- residue. This O-, alcoholic O-, is a very potent nucleophile, able to attack the carbon atom of the beta-lactam ring, you see, and it is able to open.
Which one, Professor?
It is represented by a serine residue, alcoholic O- group. You can imagine if if you take away the proton from an alcohol, you have an O-, and this O- is a very potent nucleophile, able to attack, in this case, and to open the beta-lactam ring. We know the chemical structure of this type of enzymes. We know that the active site is present on a very hindrance chemical features, so the protein is very big. And so it is important to have electronic clouds around the beta-lactam rings in order to defend the beta-lactam rings from the activity of this particular enzyme. Okay. Beta-lactamase inhibitors. Perhaps it's better if I describe these compounds tomorrow morning because they are very important. So today we have seen cephalosporins, and we have already seen how it's possible to simplify the chemical structure of cephalosporins, and the inspiration of this modification derived from natural compounds. So once again, you understand the importance of natural compounds to design new, in this case, antibiotics against resistant bacteria. Have you any questions? Yes, please.
More like a curiosity. Most of these antibiotics were once isolated from a species, natural species. Were they all bacteria?
Oh, yes, but when you want to design new antibiotics, we need a starting point. And this starting point can represent by natural compounds. So, for example, in 70, we have isolated this type of molecule. This type of molecule demonstrated a very active activity, but, for example, it is not stable. It is difficult to synthesize because if we start from natural compound, we cannot have big amounts of this compound. It's difficult. And if you understand that we need tons of this compound for the treatment of different infections. In this case, we can have an inspiration from the natural compound. We try to modify this compound in order to be able to synthesize this compound in a lab, in order to have big quantity of this compound. Do you understand? So I can have an inspiration from the natural compound, but we have to modify it in order to have a big amount of a synthetic compound. So perhaps the chemical structures can be old, yes, I agree with you, but we can modify this old structure in order to have potent compound. We can modify it synthetically in lab in order to have a more potent compound, and second, in big quantity. This is the two important points, yes, the two most important points. Activity and quantity. If you have only a compound very active but not in high quantity, okay, perhaps high price, but we need tons of this compound. You have seen for the treatment of COVID-19. Now there are important inhibitors of proteases, but it was difficult to synthesize at the beginning to have big quantity of this compound. And just now, in a hospital, we have a treatment for 20 patients, 25 no more. And so there is a limitation.
They're being used in a very low amount.
Yeah. And there is a limitation.
They just discovered the desktop because I only once heard about that medicine and no one ever talked about it.
Yeah. Okay. Other questions? Okay, so see you tomorrow morning, 10 o'clock, we start again with our new lesson. Okay, have you a nice evening?
So 10 o'clock, right?
Please,
10 o'clock.
10 o'clock, yeah. Two hours and a half are enough, I think, of medicinal chemistry. 4 hours, it's impossible for me, but I think also for you also. Really. Arrivi. Ok.
Arrivederci.
Allora, ciao ciao.
Bye bye, prof.
Bye bye, ciao. Ciao. Ciao Terenti. See you tomorrow. Ciao, arrivo subito un attimo. Ci vediamo, ciao.